right, good morning. How you guys doing? Sorry about last week. That was unexpected, and actually, I really owe the other class an apology because I emailed you guys to let you know I was sick and not coming to campus. You guys got that email, right? Um, I thought it went to both sections, and it only went to you guys. So the other class, poor students were sitting there waiting for me, I suppose. Um, how did the Thursday go when I lectured remotely? Was that all right? For those of you who watched it, anybody miss it but watch it later? Okay, so not yet. Seems like I know there's a few people bumped out of the class who weren't EVEG majors, but there shouldn't have been that many. So I guess just a small crowd today. All right. So last time we were talking about, so this was Thursday, we were talking about mass balances. We got to this point, and I'm going to pick up here in a moment, but I want to quickly touch base about the syllabus first. So now that we've had 2 classes canceled, the first day for power and a week ago for COVID, I'm really going to try to make up time in 2 ways. One, just trying to get a little bit more quickly through, wrap up the mass balances and get into sedimentation today. There's also a small section on what is drinking water treatment and kind of what are our principles there. So I'm going to try to get through that. And then the other thing I will do is, rather than taking a class period as I typically do for going through homework solutions and kind of doing an exam review session, I'll probably do that virtually, like I did class on Thursday, where you guys can ask me questions and I can go through the homework solutions, give you an exam review, answer anything like that. I'd probably also save a few minutes during class, the class period before the exam, for any kind of practical questions about how the exams look, things like that. But that's currently my plan. So if you've got some ideas or concerns, please let me know. So hopefully we can get back on track that way. And if not, if I'm feeling like we can't do that, I'll let you know. But that's the plan. Okay, so last time we left off here, I believe, where we derived some mass balances for kind of a couple of examples, a 0 order and 1st order decay. We did it for a batch system, and then this CSTR system. So we wrote up these notes. Those are posted online. I just have a fresh set here, because what I'd like to go next is actually to take a look at non-steady state systems. I think I probably didn't mention it much last time, but what happens when we have a scenario let's take the CSTR for example, where we have some water flowing into our reactor. It has some volume, some concentration here, and some reaction happening, and we have C going out with some flow rate and something coming in, C naught, some flow rate. So if that's our system, then what happens if suddenly we were operating at steady state for a long time and suddenly we change the amount of stuff coming in? That's going to cause, at least for the next period of time, for the concentration inside the reactor to be in flux, right? It's going to be changing, probably decreasing. If we suddenly added a lot more feed to it, then we'd be suddenly increasing the concentration in there, but it wouldn't be instantaneous, right? It would take some time for the system to reach a new equilibrium. So that's kind of the question here. What happens to C, and can we get C as a function of time with a mass balance? The answer is we can, and the thorough answer is sometimes that will take a little more calculus than we would like, but that's certainly doable, and I want to show you the process. I'm not going to focus hard on that in the class, but I want you to be capable of approaching problems that are not at steady state, specifically capable of recognizing how we approach it from a mass balance perspective, right? So for a zero order decay reaction, for example, where our reaction itself can be described as dc dt equals negative k times c to the 0 power. That's our zero order reaction. A mass balance would look something like this. In our volume, we're looking at some accumulation of C as a function of time, and that's what we're interested in. And in a non-steady state system, that's the piece that can be changing rather than being zero. We have our inputs, QC naught, minus our outputs, QC. And in this case, since it's a decay reaction, we have in that volume some rate constant. We're basically putting this thing in here. C to the 0 goes to 1, so we'll just leave that as Vk. Okay, so take a moment and see if you can solve that for C as a function of time. At least just the first step or two. All right, so just stop you here, and if you just start to simplify a little bit, we can divide everything by v. That way we get our dc dt kind of by itself. Get the c over to the left side to start looking at it from a point where we can separate the c terms and have some integration accordingly. And then we'd send dt to the other side. But at this moment, we get a little stuck compared to what we've seen in the past and what we kind of maybe conveniently can do. And what we'll probably require here is some sort of what we might call U substitution, or some sort of substitution of a parameter to say, okay, this is going to be in the place of C. We can do this on this 1 plus C or whatever we need to do in order to integrate it properly and take care of it. So we're going to come back to that in the next slide just as kind of an example what that might look like. But this entire setup will look very different depending on the type of conditions. So we'll probably see a homework example at some point, possibly I've used it on exams before, a scenario where we'll take a look at a stomach and you consume a hamburger and then there's no more inputs aside from a little bit of acid coming in. So it kind of becomes, it's like an instantaneous input of a hamburger and you're digesting it and tracking how much hamburger is there. And then you have a CSTR of just a little bit of acid. It's not bringing any new hamburger in, but it's taking some hamburger out as it goes, through. And so there's some question there about, well, what's the concentration of the hamburger in the stomach as a function of time? And we have no more input, and so it's not at steady state, but our mass balance, when we write it up, is very interesting because in that particular case, this goes to 0 even though there is a flow rate because C naught was 0. And so depending on how you set up a system, this will change. And in that particular example, because the C naught goes to 0, the math actually becomes a little easier and it's a little more manageable. So we'll revisit that and we'll come back to and actually that's a first order decay reaction. So pardon me there. But the point is, this will depend a lot on what the system actually looks like, what happened to the system that caused it to not be at steady state. So we'll revisit this. I want to take a moment to do the same thing with you here for a first order decay. Here, our mass balance setup would look very similar. The only difference being that we have C to the 1 power, right? So when we say we've got Q, C naught coming in, QC going out, minus VKC here. So now we have 2 C terms, and I'm going to go ahead and kind of start with the same approach, divide everything by V. We could, by the way, call this 1 over theta, because Q over V is inverse of V over Q. Okay, so then we could add these guys to both sides and have 1 over, I should have said theta, I'm sorry. One over theta times C plus KC equals 1 over theta C naught. Okay, so we could have something that looks a bit more like that. We could probably even separate out the C here, say dC dt plus C times 1 over theta plus K equals 1 over theta C naught. Okay, and then find the right way to integrate from there. And both of these, by the way, look pretty similar. We just have to have the proper integration right there. Okay, so before we actually get to that, let's have a little reminder here for integration techniques. And I may even need to spend some time with this, give you some more time with this later. I don't remember exactly how many notes I've got on this. We can certainly revisit it if needed. But okay, we have integration by parts. So this is kind of what we've been doing in terms of the integration of, we take the integral of dc, something something dc, and on the other side something something dt, right? We've done that. And so in a case where we have the integration of u dv, we can say that's equal to u times v minus the integration of v du. So that gives us this u substitution property where we can take this integral and kind of parse it out a bit in order to simplify some system. Here we go. So we're going to take a look at this example here, the step function response, as a way to kind of visualize it a bit. So if we have flow coming in, QC1 here, or C initial, flow going out, QC, some control volume with some concentration, we have a decay coefficient, so meaning we have a decay reaction, and a generation coefficient, so we have some sort of growth reaction. So two reactions in there. So this example says, so far we've computed steady state concentrations in environmental systems contaminated with either conservative or non-conservative pollutants. Let us now extend the analysis to include cases that are not steady state. Quite often, be interested to know how the concentration will change with time when there is a sudden change in amount of pollutant entering the system. Or, we could call this a step function response. So if we were taking a look at the concentration of some pollutant in our system over time, what's happening is we are at steady state for some time, and then suddenly we have a decrease, and then we reach a new steady state. Or it could be in some sort of increase, right? It could go the other way. The point being, we might be really interested to know when, in this scenario, do we cross some sort of threshold? And so how long do we have to wait until we reach that threshold? Or what happens if we're 10 minutes in, where are we now? So in this type of a case, we can typically find C at infinity. Given the new situation, we can probably calculate, well, it's going to reach steady state eventually, so we can make some assumptions and figure out, well, what's this new concentration at infinity? And we can do that, for the initial conditions where we were at previously and where we expect to be later. But then we want to find that C at some particular time. Okay, so this is what it would look like. And this is actually coming right back to what we were starting to work on here, right? This first order decay, maybe a first order growth, some sort of reaction in a CSDR. How do we solve that? So here we go with the V dC dt, QC coming in minus QC going out minus VKD times C. And here what we notice is we have the times C to the 1 power for the decay reaction. And for our growth reaction, it has K for generation times V with no C. So this would be C to the 0 power. So before we even look any further, what we just noticed from their problem setup, they didn't tell us this, but we know the decay is first order and the growth is 0th order because of the way they put that into our equation. So you see that? There's a C to the 0 power, so a 0 order growth, and a first order decay. So this is what I'm talking about when I say you should be capable of assembling this mass balance based on what you're given. Now, of course, if they wanted us to solve this problem on our own, they would need us to tell us that. But given their formulation, we can derive that, or we can write that. Okay, so let's see how they do this. They take that equation and they say, well, if we have C at infinity, we can probably calculate that by setting this to 0 for the case of C at infinity, and then solving for this C here. Both of those would be C at infinity once we've reached steady state. So we'll say C at infinity equals C at steady state. Okay, so if we take a look at this and we were to solve this for C, setting the left side to 0, I expect this equation will make a lot of sense, right? We could probably get there. Let's see, if we added the QC and the VKD C to the left side, then we extract out the C, we would be dividing by Q plus K VKD. So yeah, that would be pretty much exactly this. So that's the derivation for that point, is setting that to 0. Okay, so once we have some sort of value for C at infinity, then they go on to say, all right, well, dc dt equals, and here they're taking this term, divide everything by v. So you see they've done that. They've also separated out the C term. And instead of putting in the normal C's, what they're doing is they're making a substitution for C at infinity, because they just solved this. This is C at infinity, an expression for it. And if we back up a step, I think we can kind of see what's going on here. Let's see. So what they've done here is they've taken this Q over V plus KD that's coming from the Q in the C here if we divide it by V, and the KD here if we were to divide that by V. Those two terms are terms with C in them, so they've extracted those out. So they extracted the C out from that and multiply that by, instead of putting in C for the integration, they're doing C minus C at infinity. I thought I had some notes that were elaborating on that. I apologize for that. Actually, they're just below. So if we take a system, and so this is a little bit backwards here, but if we, instead of saying C, let's put in a substitution and say, we're going to say Y. So Y initial is going to be C naught minus C at infinity. So that's what they're doing right here, is setting up for that. Here we see it says one way to solve this differential equation is to make a change of variable. If we let Y equals C minus C at infinity, and then Y naught would equal C naught minus C at infinity, then we can solve it saying, okay, well, we have this equation, but that's not very convenient. We don't really have a good way of dealing with that directly. So let's do that change of variable and call this itself one variable, Y. Then we can treat it like we've done in the past, divide both sides by Y. We get dy over Y, and we know what to do with that. So you see that they're saying here, if we have some change in C minus C at infinity, that's the same change as a change in C. Okay, because C at infinity is a constant. Changing the C one way or the other is going to change the system. Okay, so then defining it as dy dt instead, now we have this equation, which is much more comfortable. As you see, we do the integration of y naught to y of dy, and they should have divided both sides by y there because of that. So then we get this integration here. As we've seen with the batch case, we just have a little bit of extra parameters up in the exponent here because those carried forward from that. Okay. So that gives us a way now to solve our system where we know y equals y naught times e to the minus kd plus q over v times t. And since c minus c naught is what we have for y, we just put that in, and at c naught minus c infinity is what we have for y naught. We put that in, and then we solve for a function of c. Okay, so some reminders were required here, even for myself, as you saw. It's been a little while since I looked at this. Apologize for not being clearer, but it's something you've done before, something that you can do. It's not something I'm going to task you to do an elaborate system like this on an exam, but I want you to have the ability to set it up and to work with it from there. So perhaps on an exam, I would be happy to ask you to set it up for an integration and describe what it would require. Perhaps something like that. Okay?
When you say what it would require, what do you mean?
If you were to get it to, let's say, this point here, I would, maybe I would task you with saying, okay, what does this integration look like given the situation? Set it up as a function of dc dt, and tell me what you think the next steps would be. Something to that effect. All right. So let's see if we can do this. Coming back to our zero order decay in a CSTR case. And then we'll get moving on from here. So we have in some volume our change in concentration per time equal to what's coming in minus what's going out, plus our reaction term, which is a negative zero order decay. So Vk times c to the 0. And we want to integrate this. So we'll set a little reminder here to say that we may be interested in solving for c at infinity. So we'll come back. Actually, we can do that real quick. We'll say 0 equals q c naught minus qc minus vk. So I'm just going to add qc to both sides. And I'll go ahead and divide by q as well. So c is going to be equal to c naught minus v over q, which is theta, times k. So c at infinity then is equal to c naught minus theta k. And this is just what happens if you leave this system go for a very long time, right? We'll eventually reach this. That's when I say we'll eventually reach that, that's really the definition of dc dt reaching 0. Okay, but for our case before we get there, we have this system. So dc dt equals q over v c naught minus qc q over v c minus k. So we could add, or let's say, we could add the q over v c to both sides. But let's take a moment before we get too far ahead of ourselves. Over here, what they did was, before even moving anything to the left side, they collected stuff so that they could say, okay, well here, this thing is our y. And they set that up. Let's see, how did they get the c minus c at infinity? Where did that come from? So the c, so they went from v dc dt equals all this. They extracted out the c, and I think they just said, let's treat this as c minus c at infinity. But why would they do that?
Well, isn't that expression of QCI, isn't that already like set up there? Like C infinity equals
sorry, the QCI here.
Yeah, like they just put the C infinity in for that expression because it's what equals to. Because it says up there C infinity equals that expression.
Yeah, so the C infinity here, yes, that is what they're putting in right here. But yeah. So this part I see that they're putting this in here in the right there. But what I'm trying to think of is, does it make sense that they took this equation and said, like, where did they get the C infinity in the first place? And I'm just kind of questioning myself here. So is that the C initial? I don't think so, right? That would be, should give myself some space here and work it out. So when they extract out a Q over V plus KD, what they're extracting that from, well, they're bringing a C out, but also this C initial. Where's that going? That's just, are you guys tracking with what I'm trying to figure out at all? Okay, so I'm gonna, let's see, I need to write this out again. QCI minus QC minus VKC plus KV. So they went from here to extracting out a negative Q over V. Well, they also divided everything by V, so. So if we divide everything by V, then from there, they're getting this expression. So if we divide, if we extract out a Q over V times plus KD, that's from these two terms. So from those two terms, we get C times Q over V, so negative, plus KD. So I can see those two, but we're still left with this Q over VC initial and the plus KG. So I'm a little confused by where they went with this. And again, I apologize for that. So I'll try to come back to this next time to figure that out with you. For the moment, yeah, I feel like I did this last time too. For the moment, I'm going to pause here and just resume that when I can give you a clear answer and way forward. You see that, you know, I have some sympathy if you're not recalling your calculus as well as I am, which I'm not. All right, so we'll come back to this. It should be something that we can all do. It's just a matter of reminding ourselves, okay, what does this actually look like? How do we put this into practice? All right. Second order scenarios, we actually can do this as well. It also gets to a little bit of calculus that's, you know, if we're doing steady state, it's not so bad, and it's just another one of those we remind ourselves about, like we did with the first order. So real quickly, in a batch or CSTR, here is kind of our examples. We'll just write it up and look at what this looks like. So in a batch system, V dc dt is going to be equal to negative kc squared in that volume. So here, dc dt equals negative kc squared, and we're looking at an integral that looks like dc over c squared from c naught to c, and negative k dt and so on. Now, if we look this one up, which we have a nice table for, this is the one that ends up giving us a 1 over C naught minus 1 over C. We're just going to skip ahead to look at that. If we do the integration for this right here, the second order, it gives us this equation, 1 over C minus 1 over C naught, I think I said that backwards, equals our KT. So that's from calculus, not requiring the U substitution stuff, just requiring us to remember what the integration of dx over x squared is, right? The right side doesn't change. That's simply the integral from 0 times 0 to time t and gives us kt. Okay, so we have that equation there. That would be our batch scenario. And for a CSTR, we can imagine we're going to say this is at steady state. So this v dc dt. Of course, we could go with not steady state. That's probably going to get complicated. But let's just take a look at this. QC naught minus QC minus this second order decay is going to be VKC squared. So here we can get our C terms together. We have VKC squared plus QC equals QC naught. So we could divide everything by Q. That would give us theta KC squared plus C equals C naught. And from here, it's looking a lot like we're going to have to do some sort of quadratic. We could, I suppose, simplify and say C times theta KC plus 1 equals C naught. But still, we're going to have to deal with the C inside there. So from there, it would be a bit of algebra and we could solve it, but that's the situation. Okay, so you now see the way to get ourselves into a spot where we have to solve some math, right? That's really the point of this. And then depending on our situation, we may or may not have a convenient mathematical setup. So in real life, either we dig up a textbook and figure out how to do it, or we might take an approximation and say, well, this system is pretty closely modeled by this other system, which is easier math to do and more practical. Some of the equations might get to a point where it's nowhere near practical computationally. And so it would make a lot of sense to make some assumption and simplify. And for the purpose of our class, I'm not here to teach us calculus. I'm here to show us that, hey, here's the calculus that we did learn. Here's why, when and why it would be relevant. So let's maybe brush up on that. Try to get our heads around. Here's how to do it right. But what I'm really interested in is us able to apply this process to a lot of different water treatment systems. Okay, this lookup table, by the way, does have good information. This is the same derivations we looked at for zero order, first order stuff, and how that would look like if we solved for C. It also has any type of reaction that is not quite an integer order. Those are pretty rare, but they do come about in certain situations. And there is some math that we can use to solve when that n is not equal to 1 and it's not equal to exactly 2 or 0 either. Okay?
So do we need to know those, or will we be given those?
Yeah, so I'm not going to give you any problems with this guy. This second order, if you get a problem, it's not going to be on an exam, so you'll have these notes or elsewhere to look up to do that. You will need to know the standard zero and first order. And these are those derivations that we went through last time. Do expect you to know those too. Okay, so let's take a look at a problem. I'm going to give you 5 minutes to take a look here. we have a polluted lake. Consider a 10 times 10 to the 6 cubic meter lake fed by a polluted stream having a flow rate of 5 cubic meters per second, a pollutant concentration equal to 10 milligrams per liter. And we've got this little figure here for it. There's also a sewage outfall that discharges half a cubic meter per second of wastewater with a pollutant concentration of 100 milligrams per liter. The stream and sewage wastes have a decay coefficient of 0.2 per day. Assuming the pollutant is completely mixed in the lake and assuming no evaporation or other water losses or gains, find the steady state pollutant concentration in the lake. Okay, so word problem gives you a lot of information here. At minimum, I hope you could set up your mass balance, but hopefully I think you can get a little further than that. Okay, so let's take a look. We've got this, this lake as a reactor. We could draw a control volume around it if we'd like. And we're given some volume for that. We then have two inputs, one coming here, one sewage, one coming here, and one output. So when I write up my mass balance, we are also told that it reached a steady state. It says assuming no water losses gains, find the steady state pollutant concentration. So at steady state, we should have 0 equals what's coming in, Q from the stream, C from the stream, plus Q from the wastewater, C from the wastewater, minus what's going out, QM, CM, and minus our reaction term. Now the reaction term we were told was a decay, so we know it's negative, coefficient of 0.2 per day. That unit per day should tell us it's a first order. If we recall, anytime we have a reaction, it should take the form of dc dt is plus or minus k times c to the nth power. N should be 0, 1, or 2, typically, and that will tell us what the units k is in. So if k is in per time units, that means to satisfy the units on the left side, c has to be the 1 power. So, or excuse me, yeah, c to the 1 power equals negative k c to the 1 power means that a per time unit works out okay. So we know it has to be first order. So that means when we write up and insert our reaction term here, that's going to be in the volume. We have a decay coefficient times c to the 1 power. Make sense? Right, so then we can get solving then. Another thing to note is the total flow rate going in is 5 plus 0.5, so the total flow rate going out is 5.5. So we have 0 equals QSCS plus QWCW. We actually have all of those parameters, so we have numbers we can put in for that. And we have a minus QMCM minus VKDC. And one thing we'll notice, the problem also said we're completely well mixed, so this thing is, stirring. That means that this C here is the same thing as saying CM. And I think the problem was asking for what is the flow rate, which we found, and what is the CM. So let's solve this equation for CM. Can go ahead and add QM, CM to both sides, and this VKD, CM. And then on the right, we'll have QS, CS plus QW, CW. All right, so then last couple things I'll do to simplify is we'll extract out the CM on the left. This gives us QM plus VKD. So we'll see here that the standard first order decay reaction for a CSTR doesn't really let us do it because we have two different flow rates. So a good example of why I want you to be able to articulate these mass balances, not just from the very standard typical scenario. But you'll also see it's very familiar with the process. Okay, so then we can solve simply by putting in all the numbers. So CS, let's see, QS was 5 cubic meters per second times the CS was 10 milligrams per liter. Plus we have 0.5 cubic meters per second times 100 milligrams per liter. Turns out both of those are 50, so that's convenient. And then QM was 5.5 cubic meters per second, plus this, the V, I think was 10 yeah, 10 times 10 to the 6th. So I'm going to write 10 to the 7th cubic meters. Times the K, which was 0.2 day to the minus 1. And there we go. So now we can put all these the numbers in and solve, but one thing you'll notice is because I wrote out the units, we see suddenly that, and we can check the units, on the denominator here we have cubic meters per second plus cubic meters per day. So we are going to have to fix that, and so we need to convert from days to seconds. And this should be, we can say 1 times 1 day per, what is it? I think 86,400 seconds. Done this conversion a few too many times. Okay, so then when we put all of that in a calculator, then we can get our answer. So I'm going to go ahead and pull up Excel to do just that. If you get an answer first, let me know. So on the top here, I'm just going to simplify a little. 0.5 or 5 times 10 is 50. 0.5 times 100 is also 50. So I'm going to say that's 100 on top. My answer is 3.49. And this should be a concentration unit. We'll double check that. Should be milligrams per liter. And on top here we have cubic meters per second times milligrams per liter on both of the numerators. So if we take cubic meters per second times milligrams per liter and divide all that by cubic meters per second, we should be in good shape. So this would be our final answer. Does that make sense? Good? All right. So there's a mass balance in practice. We're going to be doing a lot of that type of stuff. One more note here before we move too far from the mass balances and from our discussions of rate constants and all that. One of the things you should be able to do, and maybe you may or may not kind of recognize this already, but you should be able to solve K if you have some data. So given kinetics, even if you have some flow-through reactor, you should be able to collect data and figure out, okay, what is this K? Now, the simplest way to do that would be in a batch system, where the only change that you have is the reaction. It's very nice to do it that way. There's this concept that relates directly to this of half-life. So one of the things you can do is sit and wait and see how long it takes for some reaction to cause your substance to reach half. We can also plot the data explicitly and find things that way. So I want to cover both of those methods really quick, because you should have a handle on these, and you should be able to, I would like for you to be able to use these on problems as needed. So the half-life concept is really just saying, okay, C over C naught equals 1/2, right? The current concentration has reached half of what it started with, right? Maybe you started with 100 as C naught, and you reached 50, that's a half-life. You started with 2, you ended with 1, that's half, right? So what we're looking at is the time to get here. You could use a quarter life if you wanted to. It's not going to make too much difference. so long as you put in the calculations correctly. The convenient part of this is when you take, especially a first order equation, and you want to take a look at this. Zero order equations are pretty straightforward usually. They're pretty intuitive, especially in a batch case. But let's say you have some sort of a first order decay, and you want to know, okay, well, at what time point did it take for me to get to the halfway mark? If this is 0.5 and this is 1, we've got 0. Maybe that's what we're interested in, is finding that time. Excuse me. So if we take the half-life direction, we'll keep in mind that we know that our equation could be written like this: C equals C naught times e to the minus kt. And we want to know something about k, and we're going to imagine a scenario that gives us information about that. I say imagine. We're going to maybe take an observation. How long did it take till we reached half, right? That's our observation. So we could say C over C naught equals e to the minus kt. So now if we've just put in 1/2 here equals e to the minus k times the t that is the half-life, right? This t 1/2. We know that that equation should exist, should happen, we should be able to time something while observing the amount of concentration. We find that time, then we have all the knowns except for the k. So if we're given a half-life, then we actually are given both the time and the concentrations, because the concentration is just half of whatever it started with. It doesn't even matter what you started with, it's just half of what you started with, right? So the fact that it's relative in that manner, half-life becomes super useful, super convenient. So all we have to do is just take the natural log of 1/2, and that's going to be equal to minus k times time. So if we ever need to solve for k and we have a half-life, we could write that as negative the natural log of 0.5, or 1/2, divided by the time, the half-life, right? So you'll see problems occasionally that say such and such had a half-life, the chlorine decayed with a half-life of 5 minutes or whatever. Find what, blah, blah, blah. What it's telling you is you have the information to find k. And this is how I just did that, right? You've, I'm sure, seen this before. Hopefully that's nothing too new for you. Okay, so let's take a look at what happens if we put this in Excel and take an Excel route. So to find k with some actual data, we're going to have to make up some data here. I'll say we'll have time. We'll do like whatever I have in here on the sheet. And we're going to say some average value for, we'll do some sort of disinfection. So we're destroying some bugs and we're checking how much are remaining over time. And so we have some ratio, some viruses, right? So we'll start with 2.9 times 10 to the 9th, which is quite a lot. And I'm just copying whatever data I happen to have. The E, by the way, stands in for times 10 to the whatever the next number is. Okay. All right. So in order to take this data that I just entered and make it something a little bit more useful, go away. What we can do is we can, if we plotted it that way, it would look approximately like this. We'd have some exponent, but what we want is to linearize it. If we linearize it, then we can take a straight line, and then we're in business because we can take a regression of that straight line and have something nice. So we're going to do the same process here. Typically, when we work with disinfection, we will take the log base 10. We discussed last week that base 10 is convenient, or this must have been the first class actually. Base 10 is convenient because it's like, oh, 99% of whatever was destroyed. So we could use the natural log or a log base 10. Either way, the fact of taking a logarithm is going to linearize our data because, as we see, we had the exponent. So if we take a logarithm from that exponent, we get rid of it, and it becomes pretty much in this form. So if instead of plotting our data in just the raw form, we plot it in a log form, then we're good to go. So we're going to take the log of the data here. This should have been the average n. This first case, let me backtrack just a tad. So I wrote average of n over n naught. I should have just wrote the average n. So now we're going to take the log of the n over the starting n. So I'm going to say the log of this current moment divided by the initial one, and that's giving us 0 because log of 1 is 0. If you notice, what I've done is I've made it so that each cell calls back to that initial one as our starting point, and it's just calculating the log of whatever we're at the moment divided by that starting point. So that's going to be the best way to go about this. Now when we insert a table, or a graph, what we'll see, if we plot this data here, we'll take time as our x value, and this log here as our y, log of n over n naught. My data is bad. It's not linear. So whatever I did getting the data in the first place, turns out that some of it looks kind of linear, maybe early on. So probably I should have used data that maybe looked a little more like that. We'll just edit the data on the fly. And then it linearizes it. So if that was a first order decay, it would look linear once we took a log of it, which is why I fixed the data. I wouldn't normally fix the data on experimental stuff, right? That means something different. Okay. However, once we take this and we add a trend line, we can just take a linear trend line because we're plotting it this way. We display the equation on the chart. We can also force it through 0 if we wanted to. The slope of that line is our rate constant. Once we get it here, because that's how our data is changing with time. So if we want to find k and we have some data, that's how to do it. Okay, we linearize it, find the regression, that's our k. Okay, so hopefully you've seen some stuff like that before. So maybe just another reminder there on how that would look like. All right, so with that, I want to give a quick intro to water treatment generally in terms of drinking water treatment. We've got just over 10 minutes, and we'll do that and maybe take a quick look at where disinfection will be, not disinfection, sedimentation will take us, starting off next class. All right, so drinking water treatment. There's a couple obvious things that we care about, health and all that, but really probably the simplest way to look at drinking water treatment and the most historic would be to consider that really what we want to do is interrupt what we call the fecal-oral route of transmission of pathogens. So it turns out that any warm-blooded gutted animal has a lot of bacteria in its gut, and those types of bacteria are best kept in the locations where they are helping the organism, especially for us humans. If we get the bacteria in the wrong place in our guts, we get pretty unhappy. It disturbs us, it can poison us, it can infect us, all that sort of stuff. So we like to keep our bacteria how they are, where they are. We don't want to ingest something else's excrement because it disrupts all that. Sounds pretty obvious. We grew up learning to become disgusted by excrement in general, right? We have very good sanitation these days to keep us far separate from that. But at the end of the day, essentially what we're looking at is, let's imagine we have some body of water, and at some point, we might want to be extracting some and drinking some water, right? This is pretty natural. Ultimately, we want to be able to consume water from the environment so that we have water to drink. Now, the problem is somewhere upstream, there's typically some excrement, right? So somehow that's going to probably enter the water. That's no good. And so that's why we put our first barrier would be wastewater treatment. So wastewater treatment can certainly help with this. We expect it to, want it to. That's a good thing. However, that's not the full story because, we also have stick figures, animals, that also happen to have excrement, right? So who knows what kind of animal this is, but there it is. And it's excreting its waste into our water body. And when it rains, that all gets flushed into our rivers and streams and stuff. And so we really do need a secondary barrier, and that would be our drinking water treatment. Okay, so now you know I'm an excellent artist, and now you know why we treat water. Okay, but this fecal-oral route of transmission is actually quite important. This drives a lot of our regulation. This also kind of tells us why our water treatment strategies are going to look a lot different based on where we're getting our water. There are actually some cases where you could take natural water and pretty much drink it straight without any treatment. Kind of few and far between, so I don't recommend doing it often, but if you were up on the top of a mountain and there's a glacier melt, there's pretty good chances that would be safe to just drink right then and there. Might be worth considering if there was some sort of, air pollution causing some stuff in there. But if it's a once in a while thing, there's at least probably not going to be pathogens. And it's not because it's cold, right? We freeze pathogens all the time in order to preserve them in my lab. So freezing doesn't kill stuff. So don't assume that since it's been in the freezer for some time that it's clean. We need to cook it. But the process of cloud formation and glacier formation tends to be separated from pathogens generally. Sometimes there's natural groundwaters that are very nice and clean. So there's a few cases. Or maybe we have to deal with seawater and we have to get rid of just about everything, especially all the salt, which is hard to get rid of. So depending on where we're getting our water, maybe it's not all fecal-oral stuff, but we can treat it. It's largely a matter of how much energy and infrastructure do we need to treat it to the level that's required. So we'll be talking a fair bit about different sources of water, different technologies according to what kind of treatment goals we need. So a typical water treatment distribution system would look something like this, where we have some source of water, whether that be a stream, a reservoir, or some sort of groundwater well. However we obtain the water, we're going to treat it accordingly. and then send it out. Sometimes industry will take some of the water. There's a bit of controversy here with the amount of groundwater we take in Baton Rouge and the amount of that groundwater that the industry uses. It's a deep groundwater aquifer, and there's some salt intrusion from a different aquifer that's just happens to be salty. It's apparently not at all ocean brine salt. So there's some push to get industries to take from the Mississippi and treat it themselves. So they would have to pay to do that differently. At any rate, when we think of drinking water treatment for our domestic use, then we send it to houses and things like that. Ultimately, then we produce wastewater, flush it down the toilet, wash our clothes, whatever, and send it then to a wastewater treatment plant. Hopefully we have separated our sewer systems from our sanitary sewers. So our storm sewers from our sanitary sewers. So hopefully we don't have that anymore. Some cases it still exists. The problem with having all our stormwater go into a sewage is A, the cost, but B, when it floods, that means you're flooding sewage everywhere if you have flooded the sewer system. So that's not good. And then we'll treat that wastewater and send it back typically to a surface water is the most common. So that means whoever happens to be downstream, someone was probably upstream here, they're sending wastewater back into somebody else's drinking water. And so ultimately we do actually have some reuse, some wastewater reuse. It's just typically goes through a natural system first. That tends to help a bit with the sort of a natural treatment in some senses, dilution if nothing else. And then we just have to make sure that our treatment is sufficient to handle that, whatever we're getting from upstream. Of course, maybe as in Baton Rouge, we have well water or groundwater, and then we'd be having different things to consider. Is there a chance that that can get contaminated? Okay, so just a quick example. One of our historical events was beginning chlorination of our drinking water supply. It did not begin all at once, but it started to become popular, and I think the first use was something like 1908. And so here we have a popular figure of the rate of typhoid fever, which is a typical fecal-oral route in the US as a function of time. So chlorination is one of many things that really helps get rid of typhoid. By the time 1950s were rolling around, we really did not have very many cases in general at all. So good sanitation, good hygiene really helps with this. Chlorination of our water supply also really helps with it. Typhoid still is a thing in some places where there's not as good of protection of this fecal-oral route of transmission. So if you travel abroad somewhere, for example, I hope I'm going to be able to take students to Nicaragua next semester with water and wastewater treatment in developing countries. And typhoid vaccine is recommended for that because typhoid fever is no joke, and that there is a risk because it's underdeveloped. Infrastructure and hygiene practices are not what they are to keep typhoid fever really at bay. Okay, so the Safe Drinking Water Act of 1974 really set the standards for our drinking water quality. They pertain specifically to toxins and pathogens in terms of health. So our primary health standards, the primary standards for this Drinking Water Act, the health ones are enforceable. Well, really all the primary ones are enforceable because they deal with health. They include chemical, radionuclides, and microbial. So not just the pathogens, fecal-oral, that's kind of historic, fundamental basis, but clearly if there's some bad chemical in our drinking supply, that's also an issue. There was a case, I think it was Cincinnati, that was receiving water from one of the Great Lakes that had a severe toxic algae bloom a few years back, and it was so bad that their drinking water now contained this toxin, and so they had to renovate their treatment plant in order to be able to handle destruction of that toxin before shipping the water out. And so their water was unsafe for a while before they were able to do that. There are also these secondary standards. I think I mentioned these in our first class. They're primarily aesthetic and therefore not enforceable directly. So if your water is blue or brown or green, but it's healthy otherwise, there's no law that says it must be treated differently. Now, people will be up in arms and probably make a big fuss if the municipality sending green water does that. But technically, on a technical sense, it's not enforceable. So these aesthetics, they'd be taste, odor, temperature, color, and hardness would be the examples. And we'll talk more about water hardness and softening as one of our units in the second section of the class. Just a quick note about hardness. This is kind of the mineral composition. It will cause soap to act a little differently. If your water is very hard, it will be hard to get suds from your soap. And so soap doesn't act as well. You have to use more soap. The other thing will happen is you will get mineral scaling, mineral deposits on your sinks and stuff if you have hard water, because there's just a lot of mineral content is kind of what hardness is. If you have super, super soft water, it might feel like you can never scrub the soap back off of you once you've washed your hands or body or whatever. Because as we'll see in a few lectures, it causes a difference in how close molecules can interact with the surface. Van der Waals forces and all that. So it might be fun if you think for a moment where you've lived. For example, I grew up in this area, and then I spent 2 years in this area, and now we're somewhere around here, right? So I've had pretty soft water, and then up in Michigan, I lived for a couple years pretty hard water, and back here, for the most part, it's pretty soft, unless you maybe get outside of the area where we're using these the groundwater that we have here. So might be interesting to take a look, to think about it, see if you've ever felt that or seen that in your past. Okay, so to wrap up, where do we start? Next time we'll deal with sedimentation. Didn't quite get there today, but essentially a typical drinking water treatment plant will look something like this, and this is if we're taking surface water. We'll have some screen or bar rack to remove large solids. Then we're going to send it through a sedimentation chamber to remove smaller solids, because we want to use gravity. Gravity's cheap. If we can use it, we're going to use it. So that's our first or primary sedimentation. Water's going through, stuff will settle, we'll remove it. Then we're going to do what we call coagulation, flocculation. This is basically adding some chemicals to encourage particles to stick together and do sedimentation better. So we use gravity once, we encourage particles to get sticky and get together, then we do sedimentation again. Kind of feels a little bit redundant, but it's actually pretty effective to do it that way. Then typically some filtration to catch any of those particles that didn't fall out because of gravity. Then we've got it typically by that point clean enough to do some disinfection. If we had some special scenario like a toxin, like the algae bloom stuff, we'd probably put that process in about here as well. We've got the particles out of the way, it's cleaner. Then we dose it with disinfection and get it ready to send out for distribution. Even the distribution, as we'll learn, is somewhat part of the treatment process, because we want it to be able to prevent bacteria from growing or from infiltrating from the surrounding soil. Okay, so with that, we'll talk about sedimentation next time and probably get into coagulation as well. See you on Thursday.